How far is far, and how do we know when you get there? Scientists are on the cusp of seeing as far into the universe of stars and galaxies as they will ever be able to do. Now we ought to rephrase this question. So how far is far? We can rephrase these questions from an astronomical perspective. It's like how young is young, okay? And say, how do we know when you get there? So how do we know when we have seen the first object that ever existed? Now, the farther we look into space, the farther back in time we see. We are accustomed to nearly instantaneous communications on Earth, right? But for starlight, it takes billions of years for information to reach us from the remote past. Now, despite high cost, we can, like some of the first objects that formed after the birth of the universe, we can see some of those. It requires a new generation of space telescope to pierce the veil of time and space. So one is that NASA's powerful James Webb Space Telescope that performs such observations. So this observational astronomy doesn't start until about 380,000 years after the Big Bang. That was the time when the expanding fireball from the Big Bang, it became diffused enough that light could travel freely through space, and then ultimately they can be captured by the telescopes on Earth. We simply have no record, at least encoded in electromagnetic radiation, of what happened before this point. That means before 380,000 years after the Big Bang, what happened? We do not have any record encoded in electromagnetic radiation. Over the past several decades, astronomers are saying that 13.7 billion years have elapsed since the Big Bang. So we have, at one end, we have the cosmic microwave background radiation, CMB, and that establishes the moment when the universe became transparent to light. This CMB is, you can think of a frozen fingerprint of the Big Bang. Okay. So NASA's Wilkinson Microwave Anisotropy Probe, it is, in the short form, it is popularly known as NASA's WMAP. It made the first detailed measurements of minute temperature variations in the background radiation. The polarization measured in the CMB radiation that provides us the circumstantial evidence for the first stars, and their ultraviolet light ionized the cosmic gas. These stars apparently turned on just 200 million years after the Big Bang. So that is one end, the CMB. The other end, like the other end of this this time scale, this 13.7 billion years, okay, the other end, that we have the nearby universe representing today's cosmos, the thing that we can see today. So within it, and there is an ocean of Wilson spiral and elliptical galaxies gathered on the long filamentary clusters, small dwarf galaxies like idle clumps of hydrogen, and these will stay for billions of years, and before undergoing another storm of star path. Okay. So these two ends, so one end is CMB and the other end is the nearby universe, the local universe that we see. Between these two ends, astronomers have filled in the you can say the chapters of galactic evolution. Okay. So as we peer farther back in time, galaxy shapes appear increasingly chaotic. Okay. The compact and irregular galaxies of the previous years grew through accretions, collisions, and mergers into the larger star cities that we see today. Hierarchical growth of galaxies from stellar clumps to giant spirals and ellipticals. That did not become very evident until we had the Hubble Space Telescope, and it took a number of deep field exposures during the past 15 years. Hubble telescope unveiled a sea of small and peculiar and fragmentary stellar collections that dominated the universe more than 12 billion years ago. But no telescope has ever seen into the first 480 million years after CMB left its imprint. Okay. This part of cosmic history is what you can say is the missing chapter between these two ends. It is not clear how the universe assembled structure out of a cooling fireball. The puzzle pieces don't fit together as well. So scientists know that there must have been an early period of rapid change that set the initial conditions to make the universe of galaxies what it is today. Coincidentally, the amount of time a typical human spends as an embryo is roughly proportional to the first few 100 million years of universe's existence. So what do astronomers think took place as the universe continued to expand and cool following the CMB's birth? Like approximately, as we said earlier, it's 380,000 years after the Big Bang. So scientists have developed scenarios from very sophisticated computer models that takes the effects of dark matter, etc. So the universe then had a diffuse blue-violet glow, but no discrete sources of light. So a traveler would have no sense of depth of scale. So it's just a blue-violet glow. We don't get to see the sources of light. Okay, so we do not know what is the depth, where are we going, where are we standing. Then what happened is that this predominantly hydrogen nuclei, they formed. Okay, we call it the nucleosynthesis. Okay, during the first second after the Big Bang. So all these things we have not seen. It's just we are getting the ideas from the computer generated model. Okay, and it fits with the physics. Okay, they had captures free electrons, this nuclei, the hydrogen nuclei, and they create the neutral hydrogen. Once this is happening, the universe is cooling to around 3000 kelvins. Significant amounts of helium atom also existed, and traces of deuterium, lithium, and beryllium, the early elements. Now this fabric of space-time was not smooth, but rather an undulating terrain pocketed with gravitational sinkholes. Dark matter was beginning to coalesce under gravity into small filaments that grew larger and larger, and this actually formed the skeletal scaffolding of the emerging universe. The gravitational pull was strongest where two dark matter filaments intersected. And what happened is that since the gravitational pull is strongest here, the gas flowed into these sinkholes and gets compressed and reheated. So what happens when the gas gets compressed and reheated? Its density increased in these particular nodules, and pairs of hydrogen atoms then started combining to make molecular hydrogen. This molecular form of hydrogen, it's still accounted for only about 1,000th of the mass of gas in a growing clump. But hydrogen molecules radiate heat efficiently, and they cooled the region dramatically. The gas clumps grew into these huge clouds, while the temperature at a dark cloud's core, the temperature plunged to 300 kelvins. So it was 3000 kelvins. From that, the temperature came down to about 1/10 of that. What happened with this cooling is that it decoupled the normal baryonic matter. Okay, when you say baryonic matter, it essentially means that the stuff made from protons and neutrons that form stars, planets, and people, and all of us. So this baryonic matter got decoupled from the dark matter mixed with it. And this separated normal matter, the baryonic matter. This formed disks embedded in a halo of dark matter. So that is it's a basic architecture is formed. And this architecture repeats itself more than 100 billion times over the coming eons as galaxies form. So each cold, dark molecular cloud held about 1 million times the sun's mass within a diameter like 1,000th of our galaxy. Now we'll talk about the first stars. So this hydrogen cooled slowly to the point where gravity was squeezing it. Okay? And the first nodules of the dense gas began to contract. Now these primeval clumps contained how much? About 1,000 times the sun's mass. The compressed hydrogen gets compressed and it grew very, very hot. Okay, that it looked like a lot of mass to produce the gravity. A lot of mass to produce the gravity needed to compact it. Okay. So this process could only build objects with at least a few hundred times the sun's mass. So eventually the hydrogen nuclei is squeezed under this relentless crush of gravity, and it combined to form the helium nuclei. It produced enormous amount of energy. This nuclear fusion, this is a nuclear fusion reaction, creates enormous amount of energy, and that energy creates a radiation pressure that balanced this gravity's attractive pressure. Okay. So the nodule was collapsing under the gravity, and this radiation pressure is now balancing that collapse, so the nodule stops collapsing. And when that happens, a star is born. Okay. So the star is born, and this is a new chapter in the universe's history. We call it the stelliferous era. Okay. So from that time on, so now the nucleosynthesis that is happening is known as the stellar nucleosynthesis. That is now driving a sort of, you can say, chemical evolution of the universe. Okay. So stars successively becoming heavier and more complex atoms started getting produced in their cores through this action of nuclear fusion. Now, the first stars were million times brighter than our sun, and they glowed fiercely as well. So it is observed that the bigger the star is, the furiously it glows. So it was a kind of transformational event. So unlike any other that happened in the subsequent, say, 100 trillion years of cosmic evolution. So until the last red dwarf stars burnt out. Now these stars that are forming now with more heavier elements, we call them the population 3 stars. Okay. They spanned more than 100 times the sun's diameter. But since they are so big, they get burned out in just a couple of million years. Now imagine that our sun is burning for already 4 billion years. Because sun is small, it's burning for a much, much larger time. But these population 3 stars, they were about 100 times the sun's diameter, and so they are getting burned out very quickly.
These population 3 stars are so named because they were the last to be identified by the scientists, following population 1 and 2 families. The most crucial difference between these population types is their metal content. Young stars like our Sun have a mass with about 2 to 3% of metal, giving them a high metallicity, and we denote them as the population 1 stars. These were identified first. Okay. The population 2 stars are with about 0.1% or lower metallicity. They are chiefly found in globular clusters or at the central bulges of galaxies. Okay, their metallicity is low, but it is still much higher than the gas after the Big Bang. So now, unlike population 1 or population 2 stars, population 3 stars contain no heavy elements at all, but they are huge and they grow to masses several times that of our Sun, and burning thousands of times brighter, and they die faster. Their hotter cores give way to higher rates of fusion. So in some cases, reaching temperatures of a couple of say 100 million Kelvin compared to the very cool about 15 million Kelvin that is happening at the heart of our Sun. Now this interstellar gas usually is recycled and enriched, and leading to each say fresh set of stars having a higher metal content than the last one.
So before they died, what happened is that some oscillated tremendously in size, and during this oscillation they pumped huge quantities of heavier elements into the space. So we have done precise measurements, say for example supernova 1987A. Okay. This supernova was exploded in the Large Magellanic Cloud. Okay. It released about 1/10 of the solar mass, okay, worth of nickel. So just 1/10 of the Sun, that much amount of nickel it produced, and it released in the stellar atmosphere. Now a single population 3 star could release 1,000 times more nickel, so about 130 solar mass worth. Okay, so population 3 stars weighing more than a couple of hundred of solar mass, that star's core temperature would reach 10 billion kelvins near the end of its life. In such an environment, high energy gamma rays collided with the atomic nuclei, and what happens is that they create electron-positron pairs, and this particular process of generating the electron-positron pair, this process siphons away much of the star's thermal energy, and that's why what happens, a rapid drop of pressure happens within the Sun. So since this radiation pressure was holding the gravitational pressure in balance, this radiation pressure gets reduced drastically. So the stellar core now collapses abruptly under the gravitational pressure. And since it's collapsing, it is getting superheated again to extraordinary temperatures. Okay. Now this rate of this nuclear fusion spikes again with this increase of temperature, huge increase of temperature. And nuclear fusion spikes means releasing of thermal energy again. Releasing of thermal energy means the radiation pressure growing again, and that grows much beyond the gravitational pressure now. So it blew the star completely apart. The star bursts. So radiational pressure becomes so huge than the gravitational pressure that the Sun bursts. This is known as the pair-instability supernova. So nothing is left behind.
It is possible we may have already observed population 3 stars disguised as their population 2 descendants. What happens is that the star's outer layers can mix with the gas from the interstellar medium and give them a metal poor appearance. They can also self-contaminate as convection brings metals from their cores up to the surface. So last year, scientists announced the discovery of 2-mass J1808 2002 510438b, a very lengthy name for a small metal poor star in the very thin disk of our Milky Way. So it is about 13.53 billion years old, and it is one of our galaxy's oldest stars. This universe's earliest inhabitants, they might still be around. It's somewhere there in our cosmos. Then there is a galaxy CR7. It stands for Cosmos Redshift 7. It is in the Sextans constellation of the sky. It is a rare galaxy. It is among the oldest and most promising location to find objects that we are talking about. It's still hypothetical, this population 3 stars. The galaxy has a collection of blue and red stars. Now this color difference, it helps us to distinguish between star types. The red stars are the familiar population 2 family, and the blue ones are the exciting ones. So CR7 is a perfect place to find the population 3 stars. Now some researchers at European Southern Observatory have found traces of ionized helium in CR7, but no heavier elements in the regions of the galaxy. So we can say it's an ancient piece of sky over 12 billion light years away. This is something that we say this phase reionization. It is also attributed to population 3 stars.
Now these population 3 stars and somewhat smaller populations 3 stars, what they do, they evolve more slowly, and they eventually exploded as traditional supernovae. And when they explode, they leave black holes which are 10 times the solar mass. The shock waves from these detonations of all these population 3 stars, they compressed the surrounding gas clouds, and this compression of gas clouds creates a second wave of star formation. And this second wave, this second generation, so-called the second generation of stars, these are very, very different. The lives and deaths of their massive predecessors, during the short lives, this population 3 stars flooded the universe with intense ultraviolet radiation. And ultraviolet radiation, what it does is it ionizes the gas. Ionization essentially means that it is breaking apart the molecular bonds. So, and these population 3 stars are dying, their catastrophic death. It seeded the space with heavier elements. So, first of all, it ionizes the molecular bonds and it produces a lot of heavier elements. That these heavier elements appear in this second generation star, this new generation star. And this changed cosmos, it could no longer fabricate these monster population 3 stars. Okay. Now these heavier elements, what they do, they played a very key role. They cooled the gas clouds more efficiently because they absorbed the heat generated by gravitational contraction and re-radiate that into the space. So the gas gets cooled much more efficiently. So it's like running auto engines, okay, that transfers heat to the circulant coolant and then to the radiator. And this disperses the heat to space. So this kind of cooling, this allowed the clouds in the early universe, the universe that we are talking about, the time of the universe that we are talking about. This cooling, this allowed the clouds to fragment more because smaller clumps had enough mass now to overcome the gas pressure. What happened? The result is the stars with mass of our sun and smaller now could form in this second stellar birth wave. Okay, still, this next generation of stars had smaller amounts of heavy elements than the oldest star, these so-called the population 2 stars. These transitional population 2.5 stars, you can say, like that would appear ultra blue, and they are with the surface temperature of 50,000 to 80,000 kelvins, little more than half of their population 3 parents. Okay, so population 3 stars, and now that we are talking about these stars that got generated from this population 3 stars, which are saying that it's a kind of population 2.5. The population 2 stars are the oldest star that we can see now in the Milky Way galaxy. Now this population in between stars, the stars that we're talking about, so-called population 2.5 stars, they gathered in tight knots. These knots are the initial stage to the formation of the spiral and elliptical galaxies that will form in the coming billion years. So how far back can astronomers peer to confirm these theories about the birth of these first stars and galaxies? So we probed the early universe, okay? And in doing so, scientists have pushed the Hubble Space Telescope to its limits. They have improved the light output of this extraordinary faint blobs of light, some glowing at nearly 30th magnitude, which is very faint, from the very deepest observations of the universe. Now this longest Hubble exposure, so when you want to gather light from very, very faint universe, you have to expose the Hubble Space Telescope for a very elongated period of time. So these longest Hubble exposures reveal compact clusters of blue stars. Now this blue refers only to the light that they emit. So we have to remember this cosmic expansion shifts the inherently blue light to the red end of the spectrum. So when we see blue, that means that they are even bluer, and blue signifies that their temperature is much, much bigger. So basically that they must be extremely deficient in heavy elements. Okay. What we have talked about, the population 3 stars. So just suggesting that a link to their origins from the first stars. First stars, like, we cannot see. In no way we can see the population 3 stars. So this kind of gives them a nearly primordial characteristics. Okay, so we are seeing huge changes within a roughly 100 million year period. So if we go a little bit farther back, then what we are going to see? So we are going to see even more dramatic changes. Now these Hubble data have got a precipitous drop in the rate of star formation near the limits of these deep exposures, and it is running out of photons. Running out of photons means that there is not enough photons to build images. So very faint blue light from even earlier clusters and galaxies. What happened now with this? So we are seeing now this light has been stretched. The redshift has been so much that this light has been stretched by the universe expansion to infrared wavelengths, and infrared wavelengths Hubble cannot see. So now this James Webb Space Telescope, the infrared successor of Hubble, the largest and most complex space observatory that is ever built. It has about 6.5 meter segmented mirror. What astronomer can see, the astronomer can reach a remote era between 200 and 500 million years after Big Bang. So the reason that we couldn't see stars from this era is that the light is getting stretched to infrared wavelengths because of the universal expansion, and we couldn't capture the infrared wavelengths by Hubble. So that's what James Webb will be able to do. So scientists plan to build much larger ground-based telescopes. Now, these instruments will not be able to overcome Earth's infrared sky background. Okay, so atmospheric heat is there, so which will create an infrared sheet beyond which it cannot see the infrared starlight. So this atmospheric heat will drown the very feeble light from these what we call the protogalaxies. Okay. So only James Webb will be able to see the faint glow from the star clusters, now dating to a time younger than 480 million years after the Big Bang, which is the time that we started with. We started with about 380,000 years, but so they should look extremely blue and compact and show no evidence of dust. Wave spectrometers can analyze these brighter ones and measure how deficient they are in heavier elements. So if they are deficient in heavier elements, we can confirm that they are the hypothesized population 2.5 stars that we talked about so much. Now, depending on how bright embryonic galaxies are, some 200 to 250 million years after the Big Bang, the Webb target may be spread sparsely across the sky. So the youngest protogalaxies also should be very brightest, because they form the densest pockets of dark matter and thus has the most mass. But population 3 stars are still out of our reach. We predict that they would glow at an apparent magnitude of about 37 to 1,000th of the brightness of the dimmest object that James Webb can view. So even if James Webb can see population 3 stars, it would be like a needle in the haystack search, because they're spread so thinly. So our estimate is that we expect only about one population 3 star in a cube 1 million light years on the side. So 1 million light years cube in such a volume, we would expect to see one population 3 star, which is extremely difficult to find. So therefore only a few would exist within a volume equal to today's local group of galaxies. The black hole remnants of these population 3 stars should also be around. Okay, so there is a slim chance that James Webb can detect a population 3 star if it aligns precisely with a foreground galaxy or galaxy cluster. The intervening object would gravitationally lens the star, and then it will cause it to appear much brighter. So the population 3 star is a faint star before which there is a foreground galaxy or a galaxy cluster, and this galaxy cluster will act as a lens, and this lens will concentrate the light of the very faint population 3 star to a brighter object, and that is something that we will be able to see. Or James Webb might catch one exploding as a supernova, okay, if the time matches. But actually seeing the first star would require 100-meter infrared space telescope, and that too located in the asteroid belt or beyond, where the glow from the interplanetary dust is much fainter than it is in the Earth's vicinity. But nevertheless, the astronomers likely are it's probably completing the final chapter in this narrative. And just about 30 years ago, observers could clearly see only halfway across the universe. Hubble Space Telescope rapidly took us into the undiscovered um, sea of adolescent galaxies. Right, could see that. And Hubble's observation, what it does, it has encouraged various other space telescopes, or the great telescopes, so as to say. And this has given us more and more inputs about how the older stars would look like. So, and surely there will be a lot of exciting things for the coming space projects, telescopic projects that we have uh, for in future.